And this is the video where we talk about using formal charges to find the best Lewis structure. So when I ask you to draw a Lewis structure, I will ask you to draw the best Lewis structure and then any equivalent resonance structures, which resonance is going to be our end of this video topic. So when you put electrons, like especially the lone pairs around the outside, you start to push bonds around, electrons around to make multiple bonds, you'll find that there are different ways that you can do it. Sometimes it doesn't matter which way you do it. Sometimes it makes a big difference. And formal charges are the way that we decide if what you did was a choice that helped or a choice that didn't help. So when you're looking at formal charges on a Lewis structure, you want small or zero formal charges. Those are better than having large formal charges. And then your next option is or your next priority thing to look at is that you want negative formal charges on the more electronegative atoms and positive formal charges on the less electronegative atoms. Now these are after you have followed the priorities for making the structure in the first place. So getting an octet on something that wants an octet is going to be more important than some of these rules. Okay, so we're using electronegativity to make a decision about where the formal charges go. So we should probably define it, even though we've kind of been using it for a little bit. So electronegativity is the ability of an atom to pull electrons toward itself in a chemical bond. We use the letter chi to represent electronegativity, which when you handwrite it looks kind of like a fancy capital X. The thing about electronegativity, it might sound familiar. Pulling electrons toward itself, it sounds kind of like electron affinity, and you're going to see similar trends. It's just this in a chemical bond part that is the key to defining electronegativity. That's the major difference between that and electron affinity. So when you're in a bond, which atom wants the electrons more, even though they're sharing? Who's going to pull it the most? Who's going to have a really strong pull on it? We use the Pauling scale for electronegativity. It is a periodic trend that is related to effective nuclear charge when you go left to right across a row. It's related to the principal quantum number when you go from top to bottom. And I've got some things highlighted on here. So fluorine is the most electronegative atom. And its electronegativity is 4 or about 4. When you look some places, you might see it say 3.9. It will still, whether it says 3.9 or 4, it's going to be the most electronegative. And in the bottom left, francium is the least electronegative atom. So these are the Pauling scale electronegativities for all of these different elements. And the other things I have circled on here, I've got carbon, nitrogen, right? You can see here where if you go left to right across this row, even the ones I don't have circled, boron at 2, carbon at 2.5, nitrogen at 3, we're increasing as we go left to right. So the electronegativities, you'll want to think about these, look at these numbers when you're putting formal charges on and deciding which structure is the best. So the example we're going to do is NO2 minus, and we're still going to follow all of the steps to make this Lewis structure. So I'm going to first add up the valence electrons, 5 from nitrogen. Each oxygen brings 6. And now this is an anion, so it has a negative charge, so I need to add an extra electron. I have 18 electrons total to work with. Nitrogen is in the middle. It's listed first. It's my central atom. The oxygens are connected to the nitrogen, so they're on the outside. I draw my bonding pairs to connect them. Then I put electrons on the outside atoms. So I'm going to put electrons on the oxygens until I can't put any more. So I've got 2, 4, 6 on my left oxygen. I can't put any more on that oxygen because it also has a bond, and that gives that oxygen an octet. So then on the right oxygen, put my 6 lone pairs. Now, if I count the number of electrons I've used so far, I have used 8 around the oxygen on the left and 8 around the oxygen on the right. Now that counts the bond. That only adds up to 16. I have 2 more electrons that I have to put in here. So since I can't put them on the oxygens, I have to put them on nitrogen. Now, what I'm looking at, my nitrogen doesn't have an octet. So nitrogen has a lone pair and 2 single bonds. That is only 6 electrons around nitrogen. So we need to get this nitrogen an octet. I can't add any electrons, but this is where I can do the push electrons to make multiple bonds. So the question is, which electrons do we push? And what are we doing, and how do we decide what to do? So when you push electrons to make these Lewis structures, you're going to take a lone pair and turn it into a bonding pair. So instead of letting oxygen keep all of those lone pairs, it's going to share them with nitrogen so that nitrogen can feel like it has an octet. So first of all, we can't take the lone pair on nitrogen and share it with oxygen because oxygen already has an octet. So until we say otherwise, with the reasoning why we can do it, we cannot violate the octet rule, which means we cannot go above 8 electrons, period, whatsoever. So I can't share electrons with oxygen from nitrogen, and I cannot share from both oxygens. So if I tried to push the electrons, a lone pair from oxygen on the left and a lone pair from oxygen on the right, my nitrogen would suddenly have 10 electrons. So I have to pick a side. Which side? Who knows? Let's try both and see what happens. So if I move the electrons from oxygen A, so one of the lone pairs, and then I have an arrow showing that it's going to go down and be shared between the oxygen and the nitrogen. The result, and instead of writing a regular reaction arrow, I've got a double-headed arrow here. This arrow means that it's resonance, which is, we're going to define resonance structures, but right, this means all I did was move the electrons. I didn't move the atoms. The result that I have is my oxygen on the left has 2 lone pairs, and then a double bond to nitrogen. Nitrogen has a lone pair and then a single bond to the other oxygen, which has 3 lone pairs. So this is structure A. Right, the next thing I would need to do is calculate my formal charge and check the electrons. So we'll save that, and we'll do that in a little bit with the other structure too. If I decided to instead push those electrons from oxygen B, it's the same thing but on the other side, right? And notice I've labeled these structures differently because my atoms are not moving. My structure itself is not flipping or rotating in any way. Only the electrons are moving when I do this. So I take a lone pair from the oxygen on the right, I move it down to become a bonding pair, and my result is that now the oxygen on the right has 2 lone pairs and a double bond to nitrogen. Nitrogen has a lone pair and a single bond to the oxygen on the left. The oxygen on the left has 3 lone pairs. So pause here. If you would like practice calculating these formal charges, what you should find, all right, so if you didn't pause now, and welcome back. So what you should find is that nitrogen, with a total of 3 bonds and a lone pair, has 0 formal charge. The oxygen with 2 lone pairs and a double bond, which is the oxygen on the left in structure A, the oxygen on the right in structure B, that has a 0 formal charge. and an oxygen with a single bond and 3 lone pairs has a negative formal charge. So my final answer, like there's no like better or worse between these two structures. So if I'm looking at my structure options where either my double bond is on the left or my double bond is on the right, the atoms are in the same place. The electrons are the things that have moved, so I can relate these with a resonance arrow. I mean, every atom has an octet. My formal charges add up to the total charge on the molecule. And the negative formal charge, if we compare the electronegativities of nitrogen and oxygen, oxygen is more electronegative. So my negative formal charge is on the more electronegative atom. So they're both the best structure. So in this case, what we have is a final best structure, but we also have an equivalent resonance structure. So what it means to have a resonance structure, we draw resonance structures when there's more than one way to complete a Lewis structure, right? In our NO2 minus example, we could push electrons down from the left or push electrons down from the right. The electrons are arranged differently, but the atoms themselves have not moved. So they are connected to the same atoms, and we did not move them in space in any way. Equivalent resonance structures, which I've said that we have for this NO2 minus. So a resonance structure, you can have resonance structures that are not equivalent. They also don't all have to be the best Lewis structure, right? It is possible to write a different arrangement of electrons that is bad or just not as good. We're going to shoot for the best Lewis structure when we do ours, but you might see some of these non-equivalent or not the greatest resonance structures on the way. And you'll use some of them in organic, so don't be afraid of them. You get equivalent resonance structures when they have the same types of bonds between the same types of atoms. So in my NO2 minus example, these are equivalent because I have a nitrogen with a lone pair that has a double bond to one oxygen and a single bond to another oxygen in both structures. So same types of bonds between same types of atoms. All right, that's my NO2 minus. Let's do carbon dioxide as another example. So for carbon dioxide, my valence electrons are 4 from carbon and 6 from each oxygen. So I have 16 total to work with. Carbon is in the middle. I've got oxygens on the outside, connect them with bonds, put the lone pairs on the outside atoms, and after putting 3 lone pairs on each oxygen, I am out of electrons. I've used all 16. I cannot put any more electrons on this molecule, but obviously carbon does not have an octet. So I'm going to push electrons, push a lone pair to make a bonding pair to fulfill carbon's octet. So if I do this once, and what I have done first is just push a lone pair on the left down to become a bonding pair. So I have oxygen with 2 lone pairs. Now a double bond to carbon, carbon with a single bond to oxygen that has 3 lone pairs. So I've improved this, right? Carbon has some more electrons, but it still doesn't have an octet. So we're going to do one more push, and you still have 2 options here. You could choose to push electrons from the left, or you could choose to push electrons from the right. I'm going to write the results of each of these options, and then we'll use our formal charge rules to decide what's the best. Now, your brain might already be telling you, I like symmetry, make it symmetric. Well, I mean, it's going to give us a good result this time, but it won't always. So I appreciate that you like it better because it's symmetric, but it depends on the atoms that are there. So if I push the electrons down from the left, that's a lone pair on the left turning into a bonding pair. That would now give me a triple bond between oxygen and carbon, and I would still have the single bond on the right, leaving all the lone pairs that I haven't pushed. If I push the electrons on the right, that would give me a double bond on the right, and now I've got carbon in the middle, double bonds to each oxygen. Each oxygen has two lone pairs. That's my structure on the right. My structure on the left, oxygen, triple bond to carbon, single bond to oxygen. If I go through and assign my formal charges, oxygen with one lone pair and 3 bonds is a formal charge of +1. Carbon has 4 bonds, formal charge of 0. Oxygen with 3 lone pairs and 1 bond is a formal charge of -1. In the structure on the right, oxygen with 2 lone pairs, 2 bonds, formal charge of 0. I have that on both sides. Carbon, 4 bonds, formal charge of 0. So just the first rule, minimize formal charge, tells us that the structure on the right is the best Lewis structure. And there are no equivalent resonance structures to go with this best structure. So you have equivalent resonance structures when you get to the best Lewis structure, and it is possible to write it with the same types of bonds between the same types of atoms. We don't have that here. Now the structure on the left, like, it's not the best resonance structure, but it's still a valid resonance structure. It is still atoms in the same place, rearrangement of the electrons. It's just not, it's not the best choice. We've got a couple formal charges, a positive one on oxygen, right? Like, we could do better, and we did. They are also not equivalent. So it's equivalent when it's same types of bonds, same types of atoms. Here, my carbon on the left, it's a triple bond and a single bond between that and the oxygen. On the right, it's double bonds, so not the same types of bonds. So when I ask you to write the best Lewis structure and any equivalent resonance structures, I've kind of pulled out like what I would be looking for. Obviously, we'd need work. I've pulled out what I'd be looking for as your final answer. So if it were CO2, I'm looking for you to give me this structure that has the 2 double bonds between carbon and oxygen. Each oxygen has 2 lone pairs. For NO2 minus, I would be looking for this whole thing. So I would need a structure that has a double bond on the left, a single bond on the right, and a negative on the oxygen with the single bond, related to its equivalent resonance structure, which has the single bond on the other side and the negative formal charge on the other side.